Welcome to Lecture 6b, which is entitled Directional Derivatives and Gradient. Is an extension to Lecture 6a. Again, the material for this lecture comes from section 15.5 of the textbook and reading assignment 1 up to and including section 2. The objectives for this particular module are basically to develop the tools for determining the slope on a surface in a given direction and the direction in which the slope takes on a maximum, minimum, or zero value, and also examples to illustrate the calculation of the tangent line and directional derivative, and ultimately an extension of the concept of a directional derivative and gradient to more than two variables. So the concepts and definitions covered here are more or less the same to those described in Lecture 60A. The only difference in this case being that we're introducing the notion of a directional derivative and a gradient for more than two variables. As usual, the second slide is just an outline of the material to follow. I would ask the students just to go through it, and otherwise we'll just move on to the next slide. All right, so here's a graphical representation for the derivation of the directional derivative. And so the difference here, when you compare it to that of the computing partial derivatives, is that you can take in any particular direction. In other words, you're not forced to go along the x-axis or along the y-axis. You can basically go in it any which direction. And so you perturb the x and y at the same time. So if you look in the top left, you'll notice here that basically the operating point in the xy plane is AB. So you're perturbing A by HU1 and perturbing B by HU2. And you take this difference and divide by H. H basically this common multiplier that you see here. And so this just becomes basically this secant line that you see, right, between these 2 points. And as H goes to 0, then effectively what you're doing is looking at the slope of the line in a particular direction, which is dictated by U1 and U2. All right, so that's basically what we're trying to do here. And if you look at it on a sort of a smaller scale, this is sort of, again, the same thing. Here we have a slope of a line, right, at this particular point in a particular direction U. So this U basically has a U1 component and a U2 component, right? One being the X component, this would be basically the X component, and the U2 being the Y component. The U1 and U2 when put together is the U vector that you see here. And we're going to basically insist that the U vector be a unit vector, as we've discussed earlier. All right, let's go back to our original little picture yet again, and let's look at it in the context of how we defined the function on the previous page. So we're going to consider a point with a black point in the xy plane, which is this point that you see here. And we need a unit vector, so let the magnitude of U be 1, and U consists of an x component and y component. And the simplest vectors to consider are cos theta and sine theta, because if you take the square of this and the square of this and square root, it's 1. So this basically is a unit vector, and theta can go from 0 to 2 pi. So in effect, what we're doing is we're mapping out a circle. All right, so if you were to map out U1, U2 as a function of theta, you'd be basically looking at this red vector here, and it would be going around in the circle. All right. The pre-multiplication term that you see here, H, U1, H would be the radius. So if you increase H, you increase the radius. All right. So, but more or less, all you're doing with this is basically tracing out the points that you see here. Now, when traced out on the Z, in other words, you take this for the X component, this Y component, and compute Z, then you're tracing out the blue line that you see, which is on the surface. So this line is actually curved, but you basically make the radius smaller and smaller, so eventually this approaches that of a flat surface and basically straight lines. Okay, so those basically the red circle and the blue circle base has been described. All right, so now let's basically do some of the math. I mean, what is the directional derivative going to be under these circumstances? All right, so the slope of the curve on the surface in a particular projected direction, U in the xy plane, is defined as the directional derivative and is given by this expression. And in the limit, if h goes to 0, this is nothing more than dz dh. All right, so basically that's another way of describing things. And here again is the u vector, which had a x component and a y component, u1, u2, but the magnitude of this vector is equal to 1. If you look at it in this position here, this is in the xy plane, right? You're going in a particular direction, the xy plane, starting here. Right? This is a point. You're moving a certain number of units this way, a certain number of units here, and this is basically the direction in which you're going. And the length of this basically is dictated by the value of h. u1, u2 basically are the components of the unit vector. All right, so this is our starting point, that z is equal to this expression. All right, so what we're interested in is taking the derivative of this with respect to h, because that by definition becomes the directional derivative. Well, we need to apply the chain rule, because z is a function of x and y, but x is a function of h, and y is a function of h. So this just becomes dz dx, dx dh, dzy dy dh. And again, we apply that trick as we did before, that we can express this as the dot product of two vectors. So this and this form one vector, this and this form the components of the other vector. So that's what you see here. However, dx dh is u1, and dx dy dh is u2. So that becomes this vector. But u1, u2 is a unit vector. This can be described as the vector u that you've seen here. Now here, the book uses subscripts 1 and 2, and we use subscripts x and y. I mean, they're basically interchangeable. The nomenclature is different, but the meaning is the same. All right, so again, the physical interpretation of the gradient vector, let's take another look at it. So the gradient vector is both a magnitude, which is the maximum possible slope, and a direction in which that maximum slope occurs in the xy plane. And the direction is a unit vector. And so I basically written gradient of f as the magnitude times a unit vector. And so this is your unit vector. Previously, we'd shown that the directional derivative is just, you can also write it as the gradient of f times the cosine theta, because the unit vector had magnitude 1. And this would give you the slope of the curve in the direction of traversal. Direction of traversal would be determined by angle theta. So if theta is equal to 0, that means cos theta is equal to 1. That means the unit vector is lining up with the gradient vector. And if you do that, then the slope that you obtain is in fact the magnitude of the gradient vector. So that basically just restates what we had said earlier, that the magnitude of the gradient vector is the direction in which you obtain the maximum slope. Why is that? Because cos theta reaches its maximum value when theta is equal to 0. Now, if you turn around 180 degrees, instead of basically going up a hill with a positive slope, you'd be going down the hill. And so the slope would go from being positive to being negative. And if you go to an angle of theta of 90 or 270, you'd be walking along the hill, not down or up, along the side, which means the slope is 0. Why? Because cos of either pi over 2 or 3 pi 2 is equal to 0. So here is the summary then. The maximum slope of the curve at a given point is the magnitude gradient FAB if the direction of u is in the same direction as the gradient vector. The minimum slope of the curve at a given point FAB is minus the magnitude of gradient of FAB if the direction of u is anti-parallel to the direction of the gradient FB. In other words, 180 degrees. The slope of DUFB is 0 if the gradient FB is perpendicular to the unit vector u, which is the direction of traversal. All right, so we're going to prove shortly that the maximum slope is in a direction perpendicular to a level curve. And the projected direction in the xy plane in which this maximum occurs is represented by gradient divided by its magnitude. On the right, you see an illustration. I mean, here's the point on the surface. Right, this is basically the different directions you can take. You can go this way, which would mean you'd be going along the side of the hill, and this means going up or going down. So in one case it would be a positive slope, in the other case a negative slope. In these cases it would be a slope of 0. All right, so now we're going to prove that the line tangent to a level curve is orthogonal to the gradient vector. And so this is basically theorem 15.12 in the textbook. So it states that given a function f differentiable at AB, the line tangent to the level curve of f at AB is orthogonal to the gradient, provided the gradient is not equal to 0. Okay, so those are conditions that have to be satisfied. So let's look at the proof. So a level curve for the function f of x is y is given by some constant z0 equals fxy, which means you could, in principle, write y as a function of x for a given z0 constant. So we're going to let r of t be x of t, y of t, t being a parameterization variable. It's a position vector that traces out the level curve. Okay, so it's perfectly arbitrary at this point. So the vector tangent to the level curve, we've shown before, is given by taking the derivative of that position vector with respect to the parameterization variable. So that would be x dot t, y dot t. So next step would be to take the derivative of the function z, which is already expressed in terms of parameterization variables t. So x is a function t and y of t. But we take the derivative with respect to variable t and then apply the chain rule. So dz by dt would be df dx, dx dt, plus dfy dy dt. And as before, this can be expressed as a dot product between two vectors, this being the gradient vector and this being the tangent vector. All right, and so this can also be written in this form. And the gradient vector was defined this way. However, z is a constant. Why? Because it's a level curve. We said z0 is fxy. So it's dz by dt of a constant is 0. All right? So if that's 0, that means the dot product of these two is equal to 0, which means the gradient vector is perpendicular to the tangent vector. Okay? And the tangent vector basically is aligned with the level curve. So effectively, that's the proof right there. All right, so let's do some examples. This is the equation of the line tangent to a level curve. So we're going to consider the upper sheet of a hyperbolite of two sheets. So in this case, the upper half would be the positive square root sign. So z is the square root of 1 plus 2x squared plus y squared. And the question is to find an equation of the line tangent to the level curve at 1, 1. So that's on the xy plane. All right, we know that the tangent to a level curve at a particular point is perpendicular to the gradient vector according to the previous theorem at that same point. So first thing we'll do is we construct an arbitrary vector which has its tail at some point on the level curve, say AB, and its head at an arbitrary point xy. It basically can point anywhere you want it to be. And the vector between these 2 points is just the difference between the coordinates. So you end up with a vector x minus a, y minus b. And we're imposing a condition that this vector be perpendicular to the gradient vector in order for it to be a vector tangent to a level curve. Hence, taking the dot product and setting it to 0, we end up with this expression here. All right, so the next thing we do is we expand this out, right, and rearrange terms. So everything involving the variables x and y will be on the left side, and everything involving constants a and b are on the right side. So that's what you see here, and that's what you see here. And we need to take the partial of f with respect to x, which means this function, you take the derivative with respect to x and the derivative with respect to y, and you'll end up with this function and this function. The next step is to substitute x equals a equals 1 and y equals b equals 1 for the partial derivatives, and then compute the results for the partial derivatives. You end up with f partial x being equal to 1 and f partial y being equal to 1/2. The final result, after substitution for an AB into the equation of the tangent line, which is this line that you're going to see here, is x plus 1/2 y equals 3/2. Okay, so you have the f of x term preceding x, which is 1. The term preceding fy is 1/2. And on this side, a and b are both 1. This will be a 1, this will be a 1/2, so 1 plus a 1/2 is 3/2. So that's what you see here. Or rearranging this, we can say that's y equals 3 minus 2x. And if you want to know the point at where that occurs in terms of z, then all you're doing is substituting the value for x, all right, and into the original expression here, x and y, which is at this point, and you'll end up with this is basically at the position z equals 2. So that completes this example. Right, we'll also do a directional derivative example. And the problem statement here is that a surface is given by this equation, which is the equation of a plane. And it's basically this grayish area that you see here, and you can access that at this particular URL. And the position vector of the hiker's path, we'll put it in explicit form, is x, y of x, z, x, y of x. And the path taken on the xy plane is y of x equals x squared. The hiker starts at the position 0, 0, 3 and finishes at the position 1, 1, 0. So as far as the x is concerned, because that's the variable that's changing, x goes from 0 to 1. So the objective is to determine the slope that the hiker sees walking along the inclined plane. And then what we want to do is determine the slope, the level curve at which the slope is 0. So first we deal with the calculation of the slope. And so first of all we want is the position vector with respect to the surface, which I've spelled out here. You've got the equation for z as a function of x and y, so you can take the derivatives. So for instance, this is dy dx. dy dx would just be 2x. This is dz dx. It means taking the derivative of this would just become 1, plus dzy, which would be minus 4, and dy dx here. And so if you work through that, you'll end up with this being the position vector. And as we stated before, x goes from 0 to 1. The projection on the xy plane basically would be negating the z component. So the z component is just taken away. It's just what we see on the xy plane. So we end up with this. We need to calculate the gradient vector. So the gradient is just dz dx, dz dy. So that means you take just the partial with respect to x and y of this expression, right? And you end up with a vector which is 1 minus 4. And that vector clearly would be pointing perpendicular. It's an orientation vector. So it'll be perpendicular to the surface, in this case. Also the line, because the line lies on the surface. So next thing we need is a unit vector in the xy plane. So we have rxy. We need to divide by rx prime magnitude. So the magnitude of this would be square root of 1 plus 4x squared. And so this is what we've done. And this becomes a unit vector ux, uy. So the directional derivative will just be the gradient vector times the unit vector. We've computed that, which is here. We've computed that, which is here. Take the dot product, and we end up with this result. All right, so we want to basically now determine where the level curve, where the slope is 0. So if the slope is 0, we set this equal to 0. If we set this 0, we can solve for x, which is what I've done here. You get x equals 1/8. Once you have x equals 1/8, right, then basically what you can do is you can compute what the z value would be. So you substitute that in, and you'll end up with basically a value of 49/16. All right. Once you have that information, then you can express y in terms of x, which is what I've done here. And so the level curve is y equals x over 4 minus 1/64, and it occurs at a value of z equals 49/16. So just an explanation again here, the blue is the level curve. That's the one you see on top. And that sits basically on the plane. The black is the path along the surface. So this is the path the hiker takes along the surface. And red is the projection of the path onto the xy plane. So that's what you see when you project this onto the xy plane. So that's going from 0 to 1. That's from x equals 0 to 1. If we go along this path, then we're basically going along s, which is the arc length. So the distance traveled here versus the distance here, of course, will be longer. Okay, so recall from a previous slide that the path, the differential arc length, was this expression. Well, we have dy dx, and so we end up with this expression. And again, that's from 0 to x is less than or equal to 1. So if you want to know what s is as a function of x, then basically you need to integrate that from 0 to x. Of course, we're using a dummy variable here. I basically am not going to show you how the integral is done. You can look it up or do it yourself, but you'll end up with this. So for a certain value of x, you get a certain value of y. So we go from 0 to 1, and we basically sweep out values starting with a value for s of 0, and then a maximum value of a specific value could be, in this case, will turn out to be about 1.5. So we look here. This shows the slope. The black curve is basically the slope as a function of x. Okay, so this is going from 0 to 1. And the red curve is saying the same slope, it's a slope, but as a function walking along the curve path. Clearly, the curve path basically is longer. And so that's why you see in this case, it's 1.5 rather than 1. So just two different ways of looking at the same problem. So this is just a summary then basically of how to interpret this and the typical calculations required to solve such a problem. All right, so now what we'd like to do is to extend the notion of the gradient and directional derivative into higher dimensions. And so we'll consider the case of three variables. It is w is a function of x, y, and z. And if we hold w at some fixed value, then effectively what we'd be graphing is a level surface. So the gradient in this case, when we're dealing with three variables, will have three components, and they will be basically dw dx, dwy, and dwz. As will be shown in the next slide, the gradient is perpendicular to a level surface. So let's look at an example. You're asked to compute the gradient of the function w equals x squared plus y squared minus z, pointing outwards from the level surface. That function is basically depicted in the graph on the right. You can see basically the shape here. And this is the gradient that will be pointing outwards from the surface. So let's see whether or not, in fact, what we compute is in fact outwards. So we'll compute the gradient. So we take the derivative of this function with respect to x, and that becomes the x component of the gradient. Then we take the derivative with respect to y, and that becomes a y component of the gradient vector. And then dw with respect to z, which becomes the z component of the gradient vector. So you'll end up with 2x, 2y minus 1. For x greater than 0, this is positive. For y greater than 0, this is positive. And this is minus 1. So if you look at this picture here, assuming that x is slightly positive and x is slightly positive, that vector is pointing in the x direction and the y direction, but it's pointing downwards, which is in the direction minus 1. So this expression is consistent with the direction of the arrow that you see here. If, on the other hand, we would have been asked pointing inwards from the level surface, then we would have taken this result and multiplied by -1, in which case this arrow vector would have been pointing in the opposite direction, which is in this direction here. All right, what about the directional derivative? Here we'll just use the parameterized form as an example. How do you compute that for the case of three variables? Well, it's just an extension to the case that we considered for two variables, except we have now one additional vector component corresponding to the z component. So we have w dx, dwy, dwz, which constitutes the gradient vector. And we have x dot y dot z dot t. This corresponds to the derivative when we've taken the position vector. And the magnitude, which was, in this case, has an additional component now, which is the z component. So this would be ds in the w direction, and this would be essentially in some form of common of x, y, z space. It's not a plane anymore because we now have three variables to consider. So visualizing this becomes difficult, but effectively the mathematical computation is an extension to what we looked at when we considered the two variable case. Anyways, we can do the same thing as before. We bring this out and divide through each one of these terms by the square root function at the bottom. And we end up with this vector and the gradient vector. But this is a unit vector. If you basically take the norm of this, you'll end up with 1. So this is the x component unit vector, the y component, and the z component. All right, so next thing is to consider the proof that the gradient vector is orthogonal to a level surface. Again, we start with the notion of w being a function of x, y, z. If we hold w constant, then we're graphing a level surface. So first step is to choose a position vector that maps out a curve that lies on the surface. So this is very generic. So effectively, the position vector is a function of x, y, z, but we basically parameterize x, y, and z in terms of the variable t. So the next thing then would be the vector tangent to the curve that resides on the surface. Well, it's just going to be the derivative of this with respect to the parameterization variable. So this would become x dot y dot z dot. Next, we take the derivative of the function w, which is now a function of x, y, z, and x, y, and z are functions of t, which means that if we're going to take dw dt, then we apply the chain rule. Now, chain rule basically means that we're going to take derivative with respect to x, followed by dx by t, Similarly for y, similarly for z. Now, dw is going to be a constant because we're saying it's a level surface. So when we take dw dt, will be equal to 0. This can be expanded out, as we've shown before, in the form of a trick. We can represent this by a vector. This, in fact, is the gradient vector. Dot, the derivative of this, which is the tangent vector to a curve that lies on the surface. All right, so this basically then simplifies to this, which is another way of writing it. But again, as I mentioned, dwt equals 0, since w equals w naught is a constant, and it's a level surface, which implies that the gradient vector is perpendicular to the tangent vector to a curve lying on the surface. Why is this 0? Why? Because on the left-hand side, dwt equals 0. So the fact that the two dot product is equal to 0 means that the two are perpendicular to each other. Anyway, this concludes Lecture 6b. Thank you for listening.